Okay, so thanks everyone for coming along to this talk. The keynote introduced it really well because it is essentially a technical deep dive into the stack that was mentioned in the keynote. You might have to bear with me a little bit. We've had to have an emergency laptop change. So my normally animated slides are now coming out on a PDF. So sometimes if there's lots of things on a slide, I have to pretend that there's only a few things, and I'll tell you when they need to appear. Okay? Little introduction before I get going so you know who I am. So I work for DataStax. They're a company, they're kind of like the Cassandra company. We contribute an awful amount of code to Apache Cassandra, and we build a product on top of Cassandra that includes Spark, and we open source the connection between the two. So the Spark Cassandra connector that was mentioned in the keynote was open sourced by DataStax. My background before DataStax was building lots of systems with Cassandra. Okay, so I've spent a couple of years basically deprecating large Oracle systems with Cassandra systems, and then we started using Spark on top of that. So the warning sign would normally fly up afterward, but this is what we're hoping to get through in 40 minutes, and it is quite a lot. So if you're new to Cassandra, Spark, stream processing, this is going to be a very large brain dump. Okay, it's going to be quite hard to assimilate. If you're familiar with one or two of them, then hopefully you can follow quite well. But it's a lot to cover in 40 minutes. I'm going to do it by that of an example. Okay, so it's an example. It's another type of IoT one. It's about the processing of weather data. Going to introduce that. Then we're going to go through a bit of a technical deep dive into Cassandra and how the Spark connector works into Cassandra, and then show you some code, okay, and show you a Spark streaming application. So these do fly up in some crazy order, which I've now forgotten. But essentially, it was like roughly to work out who in the room does what, okay? And I come from the left-hand side of this, okay? So the online transaction processing, which you can use any kind of relational database, any of these NoSQL ones like coming out. There's a new database every week on Apache, I think. We've also got things like online transaction processing, okay? So that's being able to do things in the semi-near real-time report generation, learning from your customer data. But eventually that gets too large, and then we throw our data to Hadoop, okay? Today, we're going to talk about Cassandra for your operational database, Spark to do batch jobs directly on top of Cassandra to do your kind of batch work. But then we're going to talk about Spark streaming for kind of keeping these batch things up to date throughout the course of the day. Okay? And this is the use case. So this is a reference application that you can go and play around with. It uses Kafka for the ingestion of messages. And I'm not going to talk about Apache Kafka. That's too many Apache projects in one day. You if you don't know what it is, just assume it's just a piece of queuing software. Think of it like that. We're going to look about Cassandra for the raw storage of the data. And we're going to look at Spark streaming for ingesting the data, storing the raw data, and also building up kind of on-the-fly like aggregates. The kind of things which you could do inside, say, MySQL or Postgres if the data size was small enough, but if your data size is big enough, you can't do. But we can replace that with Spark streaming. And essentially, the end goal is to build up a set of materialized views that we constantly keep up to date that an application could read directly out of Cassandra. So though I am by no means a UI developer, I'm pretty much terrible at front ends, but I did just put a little front end on it just so you can visualize it. We can get all the weather stations out, we can get their longitude and latitude, and you can actually get software for a Raspberry Pi which can collect all the data we're talking about. But we want to keep things like this up to date. So for an individual weather station, can we keep things up to date, like the daily, monthly precipitation, even when we're talking about things at very, very large scale? Okay, high, low temperature for the year, for the month. You know, is it likely to rain? Is it likely to be windy? Should I wear a coat? So you can go and play around with this. It's on GitHub, like everything is these days. So now I'm just going to introduce the stack which this application uses. So to build something like that, you first need a database. And if you've got a small amount of data which fits on a single server, so hundreds of gigabytes, it doesn't really matter what database you pick, right? Take any one. Who cares? As soon as you start building like systems at a larger scale, then we need something different from a database. And because I've built lots of things with Cassandra and work for DataStax, we're going to use Cassandra. Okay? Who here has who's used Cassandra? Heard of it? Wow, that's changed over the last. When I first started using Cassandra, I went to a meetup in London. There was about 6 people there. And now it seems to be that it's almost becoming mainstream. So even if you haven't heard of it, you're probably using it today. Apple have tens of thousands of nodes in production. It's heavily used in finance because we're going to see why it's good for time series data. But we're going to talk about this top left corner, which is kind of storing sensor data. Cassandra allows you to store things on order in disk. You get to pick that as an application developer, which is why people tend to use it for time series, and it's why it's a good pick for this problem. Okay? However, when I started using Cassandra a few years ago, I didn't think, ooh, I've got some ordered data. I'm going to look for a database which is really good at ordered data. It was for the non-functional requirements. So Cassandra can run across many, many servers. It can run across multi-data centers. And it can scale to pretty large volumes. And you can always be assured that whatever your problem is, someone like Apple are doing something bigger, so they'll fall into the problems before you. It comes about 2 different papers. One came from Google, one came from Amazon. We're really only going to talk about the first one, which is the Dynamo paper, because what that talks about is how to distribute data. And that's really important if we're going to run Spark on top of it. Because if we've got a large quantity of data, we know we need to move the computation to the data, not the other way around. And if there's a technology which can move our computation and be aware of how Cassandra distributes data, then we can do some really cool things. Okay? Dynamo actually describes a key value store. Cassandra is not a key value store. It's what we call a wide column store. That's where Bigtable comes from, but that's not too relevant for today. What we're going to use extensively when we're trying to do analytics on top of Cassandra with Spark is the fact that Cassandra is data center aware. Every single node is like, hey, I'm in the USA data center, or I'm in the Europe data center. These don't have to be real data centers. Okay? In the example that we're going to go through, it's actually we're going to lie to Cassandra. We're going to use this data center aware feature to do workload isolation. Okay, so we're gonna segregate a few nodes of our operational database. We're not going to let our customers go to those. And we're going to run analytics directly on top of them. Okay, so this is where you can avoid that. Take all the data, shove it somewhere else like HDFS, and then do the analytics there. With workload isolation on Cassandra, we can actually do it directly on top of our operational database. Sounds crazy, doesn't it? So the Dynamo paper is pretty awesome. Who's read it? Yeah, you should go and read it. It's an awesome domain because we all understand it because it's about Amazon shopping baskets. Okay, and they concluded that that's a pretty large-scale service and they don't make a great deal of money when the shopping basket service goes down. Okay, shock horror. So they said we need to design a database differently. It was very much around fault tolerance. We're not going to talk about fault tolerance today, but the fact that we end up distributing our data across many servers and across many data centers allowed us to basically get the data distribution we need for doing this distributed computation. The 2 features of that paper that are really important for this topic are the consistent hashing and how Cassandra replicates data. Okay, every database, every NoSQL store in the world is jumping up and shouting, please run Spark on top of me. Okay, it's the hot topic, right? There's no way that people haven't heard of Spark at the moment unless you're hiding under a rock. What's really important is that you can get workload isolation and that you can make Spark and build Spark partitions that are aware of how the underlying data store, partitions data. So, what is consistent hashing? How does Cassandra do it? Why is it useful for running Spark on top of it? So if you do a full table scan on a single node database, okay, so big, large relational, a few million rows, it's going to be slow. Okay? If you've got a 1,000 node database, it's going to be really slow. So Cassandra kind of removes features that you'd expect in a normal relational database system to stop you ever having to do something like a full table scan. All right? And it does this just by taking part of your data, hashing it, and that working out which node it's on, right? And Spark can do the same. So if we have some data here, like Jim and Carol and Johnny and Susie, what we do, or what Cassandra does, is it hashes that part, the key, and then that goes to a value. Now, the real value is very big, and I can't say the numbers, so we're going to pretend it's between 0 and 1,000. So we'll pretend that Jim goes to 350, Carol goes to 998. The second piece is that each node in a Cassandra cluster owns a range of this hash range, so 0 to 1,000. We're going to say that node A owns 0 to 249, node B owns 250 to 499, etc. Okay? This means that drivers and other nodes in the Cassandra cluster can always work out where your data is. Okay? So not only do Cassandra nodes do this, but drivers do. So the driver says, oh, I'm going to store Jim. I'm going to go directly to node A. Okay? This is why you often see the funky picture. Whenever you look at a Dynamo-based system, you often see a ring, okay? And you often see people talking about hash rings and things. And it's simply because you can put the nodes in a nice ring and say, node A owns this section, node B owns this section. The reality is in Cassandra that it's actually split up vastly more into lots of little sections. And that's so we can easily scale out and scale in without having to rebalance. This basically results in a table which can easily be worked out. It's a deterministic algorithm for working out where data is. And this is exactly how the Spark connector is going to build Spark partitions to match Cassandra partitions. But that's not it. It would be a pretty terrible database if it told you to separate your data across many nodes and then it didn't replicate. Because poor old Johnny, if node A went down, would vanish, and we'd cease to ever have Johnny again. So the next thing that we do in Cassandra is we replicate it. And replication has to be clever. If you want to build an AP system from, say if you're CAP literate, you need to be topology aware. Okay? There's no point putting 3 replicas all on the same rack inside your data center. Okay? Then if you have a network partition between the racks, then it's all hidden over here. So what Cassandra does is, because it's data center aware, it's also rack aware. And if you ask for, say, a replication factor of 3 inside a data center, what it'll do is it will put a copy of your data on each rack so that you can handle network partitions between the racks, you can handle full racks going down without losing data. Okay? This is where the real animation has gone away because I'm no longer in Keynote and I'm on a PDF. So I'll just have to tell you the order at which these lines would have come in, because this is just kind of explaining the whole system of how a write works in Cassandra. So we start off with the line up at the top here. And this is the, you can just about see that. So this line here, okay? A client decides to do a write for a particular key, or a read. It goes directly to a node into its local data center, which owns that data. Okay? So it knows that it needs to store it here, and it knows that if it was reading, it would read it from there. When you do a write in Cassandra, you pick a consistency level. We'll talk about consistency levels briefly later. But essentially, if we do it at consistency level 1, then this guy here, the first node that we talk to, can return right away and say, yep, I've got your data. What Cassandra then does is this coordinator, as we call it, it's a coordinator just for this request. What it does is it replicates the data out to the other 2 replicas. And it can always work out what these are. It's a deterministic algorithm for looking for particular nodes on different racks. At the same time, the coordinator selects what I call a remote coordinator in a different data center. Okay, so here we've got 2 data centers, and we want to replicate our data 3 times in each. We only copy it over once because we're assuming that the network link between data centers is slow or expensive, etc., and is more likely to go down. It's then the remote coordinator's responsibility to replicate it to 2 other nodes in the other data center. Okay? And at that point, you have replication. The tunable consistency comes about when you want to say that request is complete. So if you want to be really quick, then you say 1 and it returns right away. If you want to wait until more replicas have the data, you can say all, right? That would be all 6 nodes. This is a terrible idea and you should never do it because you're losing all of the availability suddenly, right? As soon as a single node goes down, queries are going to start failing. More likely, you're going to start using things like quorums, which is a majority. So in this previous example, we have 6 replicas. A quorum would be 4, okay? to majority. You often don't want to do that, though, because if we were going to do get it to 4 in the previous example, we would have to go across the WAN before completing that request. That could be slow. So you have these local quorums, or local 1. What that basically says is, in the local data center, get it to a majority there. And that means that in this previous example, we'd get it to 2 out of the 3 nodes in the local data center and let the rest happen asynchronously. When Spark's doing writing to Cassandra, it's always doing things locally, okay? Because what you don't want is for your Spark jobs to suddenly start hammering your remote data center, which would be your operational, the one that, say, your customers are facing. So by default, you can override it. The Spark connector does everything at local 1, which basically means I want acknowledgements from 1 node in my local data center. At that point, I normally wave my hands and say, Cassandra doesn't have any masters, okay? Cassandra there's no single point of failure. Because when I first started learning about Cassandra, I started seeing, is that a single point of failure? Is that a master, etc.? So that coordinator in the previous example, it is not special, okay? If that coordinator were to go down, then the driver has a load balancing policy, and it would just use a different coordinator. The other node, which sometimes people think, is that one special? Does that one need to be up? Is the node which your data hashes to, okay, rather than the other 2 selected replicas. And the answer is no, if that one's down. It's a deterministic algorithm for working out the other 2 replicas, and clients can just use those 2. So that's my quickest fire introduction to Cassandra so we make sure that people understand how the Spark connector is going to work. Does anyone have any questions? I realize that we've only spent 10 minutes or so, but does anyone have any questions on Cassandra before we jump into the Spark land? Yeah.
What if all the nodes which handles one single hash are down?
So you've got 2 options. So the question was basically, yeah, what if selectively 1 replica in each of my racks was down and I can't write? You have 2 options, and it's you as an application developer that's got to decide. You either fail, or there's a special consistency level called any. What any is it gives it to another node to look after until those nodes come back up, okay? And it keeps it for a configured amount of time. By default, I believe it's 3 hours.
So it's like you change the hashing policy temporarily, right?
The hashing remains the same. It's still, those are the 3 replicas. But what you're telling the driver is, give it to another node, and that node will keep it in what's called this hinted handoff. Just for a short amount of time, you pick the time. The reason it's not unlimited is because, let's say this is happening, right? It's bad times. You've got a third of your data center down, or however many. If you do this for too long, what you end up doing is giving the existing nodes, say half of your data center, you're giving them more work. So you're almost overloading the nodes when there's half the number of nodes available. So you can turn this off, and you can configure the amount of time that it happens for. Any more Cassandra questions before we get into Spark? No? Let's move on to Spark then. So, given the keynote and the fact that no one put their hand up, that could have been because she asked, who doesn't know Spark? Who does know Spark? We'll do the positive question instead. So most people have heard of it. We'll spend a few minutes on it, and then we'll go on to the integration between Spark and Cassandra, and we'll start looking at Spark streaming. So if we were to store our data in Cassandra, Cassandra is very good at storing vast quantities of immutable kind of like time series data. If we were going to store data for, say, all the weather updates of all the weather stations in the world, it might look a bit like this, okay? Weather station ID, some time, so this is year, month, day, hour, so we're assuming 1 event per weather station per hour, and then some cool stuff, pressure, precipitation, temperature, right? This gets very big very quickly. How do we actually do some more like aggregate queries on this? Okay, how do we work out the daily aggregate precipitation? Right? Cassandra doesn't support a lot of the features that you might expect of a relational database because they typically don't scale. Okay, so the next section is going to be how do we use Spark to turn the data into something more useful? And it's at that point where I get into my defense of Cassandra. Like, why doesn't it support this stuff? okay? As I said, if your problem fits on a computer, don't use a distributed database like Cassandra. Use a relational database, okay? Use something with lots of fancy secondary indexing. If you've got this, if you've got a scale problem and you want to run across many servers, if a technology offers you behavior like secondary indexing and aggregates and all these types of things, think to yourself how they scale on 100 nodes. How do you think a secondary index works on a 100-node cluster? Okay? Wherever that secondary index might be, it has to go to that. That's going to link to many hundreds of rows in your database across many hundreds of computers. It's going to be slow. If you take, Cassandra actually does have secondary indexing. I just tell people not to use them because it works on a 3-node cluster. It might work on a 6-node cluster. It doesn't work on a 100-node or a 1,000-node cluster. And that's simply because you end up having to go to too many computers to answer your query. So if you denormalize and you duplicate your data inside Cassandra, you get the advantages of the fact that you get to hash it, you get to go directly to a single node. This works if it's 3 nodes or 1,000 nodes, and then you get to do as few seeks on disk as possible. So it's irrelevant whether you've got a petabyte or a gigabyte. The actual satisfying your query is the same. It goes to a single node, it does a couple of disk seeks, it brings your data back. It's called what I call a scalably performant query, if that's a real thing. However, when we want to do things like aggregates and analysis and things, we don't really care about a 10 millisecond response time. We're maybe happy to actually it take seconds or maybe minutes or hours or days if you're using Hadoop. Also, we want to come up with a solution to keep these things up to date. We want to maybe do stream processing. So we're not doing a query, what is the daily aggregate precipitation. We've just constantly kept it up to date. Okay? And that's where Spark on top of Cassandra comes in. This is one of my favorite cartoons. So we've all kind of heard of it. Most people put their hands up. But it's pretty much, you can think of it as a replacement for Hadoop MapReduce, right? It's a distributed computation engine with some really cool fancy bits which make it slightly nicer. My favorite part of Spark is essentially you get the same API for stream analytics, micro batch analytics, that you do for proper batch analytics. Okay, that makes my life as a developer vastly easier. Okay, and it's obviously hit the world by storm, no pun intended, because it's already in all of the Hadoop distributions, but it's not just making its way into Hadoop distributions. It's made its way into DataStax' product, which is very much an operational database. Okay? So it's useful for both the kind of business intelligence, the data warehousing, and it's also useful for augmenting your kind of operational system. Okay? And that's what we're going to talk about today. We're going to talk about a couple of the components. So obviously, Spark is not a database, right? It needs somewhere to get its data. That's typically HDFS. Today, we're going to be talking about Cassandra, all right? The general compute engine, which is the Scala API, or there's Python and Java as well. We saw some of the Java compute engine in the keynote. We're going to look at Scala today. Okay, that's a nice Scala API. It makes you look like you're just dealing with a collection, which is very nice. Okay, we're also going to look at streaming and maybe some SQL if we've got time. So RDD, you've already seen an RDD. You've seen like 3 of them already today. So I don't need to tell you what an RDD is, okay? It's just an abstraction across a vast quantity of data. Think of it as a list. It just happens to be an entire Cassandra table with a petabyte of data in it, or a very large file on a distributed file system, okay? You get to do, if you're used to any of, say, the Scala APIs or collection, kind of immutable collections in general, you're going to get things very familiar like filter and map and flat map, etc. Okay? We're going to see quite a few of those today. What Spark does when you do all of these things is precisely nothing. Okay? You do all these things, it ignores you until you do an action, something which has a side effect. And the side effect could be writing it to a file, but today it's going to be writing it to a Cassandra table. So we're going to see data coming into Cassandra from Spark Streaming, but also out of Cassandra. Everyone has to have a word count example. I'm amazed that the keynote doesn't have a word count example. Stolen directly from the Spark docs, so this is not the most exciting Spark example in the world, but it gives you an idea, if you haven't seen Spark code before, of exactly what we mean by an RDD, right? You take a file, you turn it into an RDD. We're going to see the same but Cassandra table very shortly. You can do operations like split each line by white space. map it to a tuple with the word and then 1, and then your typical reduce. Right? And if you've seen MapReduce, Hadoop MapReduce of the equivalent program, you'll realize this is pretty quite nice. There's also a REPL, right? I spent most of yesterday on a REPL working on gigabytes of data inside Cassandra, and I was just hacking away doing ad hoc queries, things I wouldn't normally be able to do with pure Cassandra, because it kind of restricts you to do only the performant queries. That example was what we call a batch job, right? You're dealing with a huge file, right? We're going to show you how to go across that entire weather data and do a batch job on it. That might take minutes. It's going to take proportional to how much data you have. That might be, quick for a few gigabytes, but it's going to slow down. That's where Spark Streaming comes in. So we get to actually keep things up to date, in the near real time, because we can't say real time because that word means something very strongly to certain people. It's not the full functionality if you're familiar with something like Storm. It's not going to process things, say, as they come on the queue. It does what's called micro batches. So we're going to see for our example with weather data, we'll show you a 500 millisecond micro batch, which is as small as it gets. So if you need results to be updated more often than every 500 milliseconds, look elsewhere. Okay, this is quick, but not the single-digit milliseconds, the kind of response times we'd want directly from a Cassandra database. So let's get onto some example code. Okay, we've got a database, we've got a stream processing platform and batch processing platform in Spark. Let's start looking at some code. So a note on deployment first. So if you're going to deploy a system like this in production, what you're actually going to do is co-locate Spark and Cassandra on the same servers. Right? If you're an open source junkie, you have to do this yourself. If you're using DataStax Enterprise, you get this by free. You just click, I want a Spark worker inside that Cassandra node, and you get it. Okay? Little shameless plug there. The reason for this is the Spark connector. Now, if you're Spark literate, you know that Spark has a thing called partition. And a partition is the level at which concurrency and tasks are executed on. What the Cassandra Spark connector does is build Spark partitions of Cassandra partitions, same terminology, it gets confusing, that live on the same node. So the connector is never going to build a Spark partition which is made up of Cassandra partitions that live on 2 different nodes. Why? So we can send the computation to the worker that's local to that node. All right? That's the important thing. If the driver did not do that, it would be useless. Back to the example. So we'll do batch processing first. So we're going to assume that the data is ingested into Cassandra by some other means, and we're going to have a look at maybe what kind of batch jobs we could run on top. Okay, remember what the data looked like? It was a big wall of numbers. This is the table. So this is the schema for the table I showed you before. When we introduced Cassandra, I didn't actually talk about exactly how you model data in Cassandra, because I thought we might as well wait to the example. So the only hard thing you have to worry about when you do things with Cassandra is selecting the primary key. All right? So this looks a bit like an SQL table. We've got things like wind direction and speed and temperature and all these types of things. The really important thing is the primary key. We're going to spend a couple of minutes on this. The primary key is exactly how you tell Cassandra how to distribute your data and how to order it on disk. Now, because you're picking how data is ordered on disk in Cassandra, you obviously can't query it in different orders, which is very important. That's why you end up duplicating. So, primary key. Looks simple enough. The primary key is made up of 2 parts. And I've already kind of explained this a little bit, but we're going to see a concrete example here. The primary key is made up of the first bit. That's the part which is called the partition key, which is hashed. Everything with the same partition key will end up on the same node in your Cassandra cluster. So any queries in the same partition are going to be quick, even without Spark, right? The next thing you pick is all the other fields which you want to be part of your primary key. They actually dictate your order on disk, right? So if you do a range query, which is for like a time period, it's going to be really quick. So if we actually look, this primary key here ends up looking on disk a bit like this. So we have a partition key, and then, I'm only showing one field, temperature, otherwise the slide would get too big. And then we have everything in order. So if you have a look here, the temperature has actually been prefixed with all of the members of the clustering column, all of these guys, okay? So we can see that the 10th, 9th, 8th, 7th. So if we did a limit query on this table, get me the last 5 events from this weather station, it's going to be really quick. Okay? If we asked for if we didn't include the partition key in our query, you'd have to go to every single node in the cluster. For that reason, Cassandra doesn't really let you do it. There are some cases where it will, but that's when we're going to use Spark to do it all. Okay? So yeah, 1,000-node cluster, we just go directly to one node. All right? This also had fancy animation, but it's all gone. So essentially, if we want to do a query which is, say, greater than 7 than less or 10, and this is our format on disk, what Cassandra will do is go directly in, start at 10, or with this indexing on file, and then slice it. And it gives you it back as a nice table. So you don't have to worry about that format when you're programming. If you're used to tabular data from a relational database, the programming API is the same. Just know that's why it performs really quite quickly. You can also just store, you don't have to use the clustering column functionality. You can just have a primary key which, with just the partition key. So an example of that is your reference data or, something where you're not going to be wanting to do range queries. So the weather station data is like that in Cassandra. Where we would start to lose out in Cassandra is when we wanted to build a table like this. Now, I've already told you can't do an aggregate style query in Cassandra. So what we want to be able to do is keep a materialized view, like a materialized view up to date in Cassandra. This one here is for the daily aggregate temperature. So it has the same primary key, but we're actually going to keep things like the day high, the day low, averages, things like that. And there's no real way to build this. Okay, you could obviously do some fancy things inside your application, but we're going to use Spark for that. Another example might be of a materialized view, in air quotes, is a daily aggregate precipitation. So constantly keep up to date with how much rain has happened every day. Okay? And we could do a batch job for that. And I'm going to show you an example. We are going to show you an example of a batch job for that. But in reality, what we want to do is with Spark Streaming is just keep them up to date forever. So if we're building like a dashboard application, it can just go directly to Cassandra, do one of the performant queries, and the Spark Streaming job is going to keep it up to date. So I'm sorry if you don't like Scala. I realize some people don't, but let's quickly just to race through some of the code. So this is actually what the raw data looks like. This is real data, by the way. It's historic data from the US. You can go and get years worth of it. This is a case class in Scala, so you can this basically is just like a POJO if you're in Java, or a struct. It's just how we're going to represent the data inside our application. So it's in the same order as the comma-separated value. You create a streaming context. This is where you select how often you want your code to run, right? Ignore the Kafka bit, okay, so just connecting to Kafka. Everything after the Kafka bit would be the same whether you're getting it from MQTT or 0MQ or from a socket or whatever. We can split the comma-separated values, by comma, and then shove it into the case class. This is actually going to give us a stream of raw weather data artifacts. And then it's our responsibility to do something funky with that. One really cool feature of the connector is that you can just, if your case class or if you've got a tuple matches your Cassandra table directly, all you do is save to Cassandra with the key space and a table name, and it will just put it in there. So even though I'm talking about stream analytics here, we are leaving the raw data. So now actually Spark Streaming has taken over our ingestion of raw data. The next thing we're going to do is keep the daily aggregate table up to date. All right? So what we can do is we take that stream. So remember, that's a stream of raw weather data case classes. We can then map it to look exactly like this table. Right? So it's got the weather station, the year, month, and day, and it's got the same primary key. Now, there's a really funky type in Cassandra, which used to be quite buggy but works really well in 2.1, called a counter. Now, what a counter is like, imagine it as a normal integer field inside a database, but every time you update it, it just adds on the value. Okay? So what this code is actually going to do is every 500 milliseconds, it's going to save all of the raw datas. It's going to map all of the raw datas into this. It's going to take out the 1 hour precipitation, and it's going to put it in Cassandra, and the Cassandra counter is going to keep it up to date. It's going to add them all up for you. So you can go to this table at any time, and it will be at most 500 milliseconds behind real time. What about a batch job? Okay, so this is what good old, this isn't streaming. This is just a regular loading a Cassandra table from into an RDD. We're selecting the temperature. Now, the important bit here is we're selecting the weather station ID in this query. Okay, what does that mean in Cassandra? It means it's going to be performant. It's going to go to a single node, right? So this batch job will actually be really quickly. You could make this as part of your operational system because it's going to a single Cassandra partition. All right? And here's an example. In Spark, you have this stats counter, which can then give you a count and means and things. So we could then save this back to Cassandra. If we don't include the weather station ID, in this example here, right, this is going to scan the entire Cassandra table. This one is going to take time depending on how big your partition is. How many weather events do you have for a particular station? This one is going to get slower as you add more weather stations and as you add more data. All right? You would not make this one part of your operational system because it has to scan an entire Cassandra cluster. This would be a batch job which you might run at night. This would be the one that you could run whenever. If you wanted to keep this one up to date, which would be the mean and the high-low for all of your weather stations, you would then write a Spark streaming job. So in the same application, you can have a mixture of Spark streaming and Spark batch jobs. Okay? So that's pretty much it. You can see here that you can easily include both. Okay? So when you're building a streaming system with Kafka, with Spark streaming, you need somewhere to put the data. Okay? I'm saying Cassandra's a pretty good solution, especially if you have vast quantities for the raw data. For the materializer views, you can put those in Cassandra as well, or you could put them in a caching system, or because there's not the data size there isn't as great. And don't forget that if you're doing Spark streaming, you can also combine it with running batch jobs on the fly. Some batch jobs, if they're in a single Cassandra partition, are going to be quick. However, the jobs which are going to be over your entire Cassandra tables with gigabytes, terabytes, petabytes of data, remember, they're going to be the ones you're going to run at the end of a day. And the whole goal is essentially to keep a bunch of views ready so this guy can just pop in here whenever he likes and see an up-to-date version of these aggregates, even if you're talking about many tens of thousands of events per second and many terabytes of data under the covers. So on that note, I am done. If you've got any questions, I think we have a couple of minutes for questions. So thanks for listening. And hopefully you have a good idea now of whether something like Spark and Cassandra would be a good tech stack for your next project.